And now for our second presentation in this session, we have Stefan Spindler from the Otto Bistheim School of Management.
Thank you very much, Alan, and I would also like to take the opportunity to thank the entire committee for having selected our paper as a finalist. It's a great honor for us to be able to present our project on fleet renewal at La Poste. This is our research team, which is involved in an ongoing stream of projects related to sustainability at La Poste. And I would like to in particular mention Paul Kleindorfer, who is seated at the center of our group, and he really is playing a pivotal role in this project. This is an outline of what we would like to cover in the next 30 minutes. I will introduce you to the context of the project. Then Andre is going to take over to explain you the details about the decision model. And then Alain from the La Poste is going to explain how they actually used it and what they're going to do about it. The postal sector faces significant challenges worldwide. A major one is the decline in mail volume, which is due to e-substitution. We're talking about a volume decrease of minus 30% by 2015 as compared to 2007 levels. At the same time, postal operators need to fulfill what is called the universal service obligation, which means that they have to deliver to remote areas, and there's plenty of them in France. At the same time, however, postal operators also face constraints in terms of increased sustainability. So there's legislation being put in place that penalizes polluting vehicles and that gives a bonus to silent and less polluting vehicles. So we can conclude that fleet operations is actually a major lever in order to achieve cost reduction, but also to enhance sustainability. Let me now give you an overview of the fleet. You can see on the right-hand side the various transportation modes that are being used. And the one mode that is relevant for our research is what you can see on top, the small vans, who deliver about 40% of mail. You may wonder, well, what happens to the remaining 60% that is delivered by bicycle or by foot, actually. Now, let me give you some numbers about that. There's 45,000 vehicles in that fleet, and those are typically leased over a 6-year time horizon. Those vehicles travel a daily distance of 2 million kilometers. And just to put that into perspective, that's around 50 times around the globe. The average daily mileage, however, is short. It's 44 kilometers. The total cost associated with that operation is 230 million euros. And there must be an alignment between geography of where the delivery takes place, the delivery volume, and the ergonomics of the vehicle in order to make that a successful operation. Now, what is the environmental record of that delivery? There's 170,000 tons of CO2 emitted. Off of that, we could save 30% if we were to introduce electric vehicles. There's a well-known concept that goes by the name of the triple bottom line: profit, people, planet. And that posits that there must be all three aspects covered in order to make a sustainability initiative successful. And this is indeed what we find in our project. There is an economic impact in terms of cost reduction, in terms of risk reduction. Secondly, there's clearly an environmental aspect, because we might be able, through the introduction of electric vehicles, we might be able to reduce the amount of CO2 emissions and other particles. And thirdly, there's a social aspect where in particular the employee motivation that goes up because of the electric vehicles is important. What are the technology options that are available right now? And before I go into that, let me reiterate the fact that total distance travel or average distance traveled per day is short, 44 kilometers. So that means that we do not face a range issue for the electric vehicles. There's an incumbent technology, which is just a standard diesel run engine, and that has a deterministic purchase price, but stochastic operating cost, mainly driven by the uncertain diesel price. On the other hand, we have a challenging technology, which is electric vehicles. Those can be characterized by a stochastic purchase price, driven by the battery price, and deterministic operating cost. Andre is now going to explain how we translated those general observations into our decision model.
Thank you, Stefan. Let me continue with the description of the model we used to solve the problem. On the left side of the following slide, you see a schematic representation of our problem setting, where the blue arrows represent the operation of internal combustion engine vehicles, which we call ICVs, and the green arrows represent the operation of electric vehicles, or the EVs, from the time of acquisition until the end of the leasing contract. Now, we limit our decision horizon to the range from t equals 0 to t equals capital T, so the electric vehicles can only be acquired in this period. Now, the question is, what is the optimal number of EVs and ICVs to be acquired at any given time? As you remember from the previous slide, current EV technology is more than sufficient for postal operations. So our first assumption is that ICVs and EVs are fully substitutable. The next assumption we make is that vehicle demand at any given time is known. Further on, we introduce two stochastic parameters in our model, which represent the battery price and the fuel price, which are key uncertainties in our model. Now, in order to answer that question, what is the number of EVs to be acquired at any given time, we formulate the objective function, which minimizes the total expected fleet cost, which you can see on the left side. Now, the decision objective at any given time is to choose the number of EVs and ICVs to be acquired at time t, which minimizes the acquisition cost at t, and also the expected future acquisition and operation costs contingent to my decisions at t. We also have further parameters that are required to fully describe our objective function. Now, in our model, we analyze 4 distinct replacement policies. The first one, which we call the ICV-only policy, which basically represents the business-as-usual scenario, is a scenario where no EVs are used and the fleet replacement is done fully with internal combustion engine vehicles. The next policy, the static policy, represents a scenario where all decisions are done in the first period of operation. Now, the benefits of such policy would be, for example, the volume discounts and reduced administrative efforts. The next policy, the dynamic policy, represents a scenario where the fleet operator has an option to always to update acquisition decisions at every period in the decision horizon. Now, the benefit of that is evidently the full flexibility due to the fact that the fleet operator uses recent uncertainty realizations. And the last policy, the policy under perfect information, utilizes complete knowledge of future uncertainty realizations. Although this is a hypothetical scenario, it still provides a good estimate for the potential benefit through, for example, further market research. Now, I mentioned there are 2 uncertainty parameters in our model. The first one, the fuel price, we model as a Brownian motion with drift. So when we use the wholesale diesel price in France since 1990, we can determine the drift rate and the volatility of the stochastic process. We also expect that the rise of the fuel price will be significant in the future. And on the bottom side, you see the formal representation of the stochastic process. Regarding the second uncertainty in our model, the battery price, we analyzed available technical reports on the prediction of the battery price in the future, which you may assume is quite challenging because battery technology in the automotive sector is still under intense development. Although if we analyze the volume-dependent and independent costs of the battery production, we expect the fall of the battery price by 65% until 2020. So this is an important conclusion in order to model our battery price process, which we represent as a mean-reverting Ornstein-Uhlenberg process. Now we know the expected price known at the time of market introduction of a certain model of an EV. We also know the long-term or the volume-independent cost portion, which is not affected by scale. And we also know what is the expected price at 2020. So this gives us important parameters in order to model our stochastic process. Further on, we model the battery price separately from the chassis of an electric vehicle. We also assume that the battery price is discarded at the end of use, and the expected lifetime of the battery, 6 years, coincides very well with the leasing duration of electric vehicles. And again, on the bottom side, you see the schematic or the formal representation of the battery process. Now, the next important parameter in the model is the electricity price. The wholesale electricity price in France since 1998 was fairly constant. And this is an important conclusion for us in order to use this parameter for our model. Further on, we assume that due to the increased base of electric vehicles, fleet operator would be able to gain economies of scale or volume discounts through further purchase of EVs in terms of decreasing electricity price. Now, when we solve the dynamic stochastic program we were faced with, we derived an optimal policy. And this optimal policy tells us to acquire only one type of vehicle at every period. And the choice on the type of vehicle is contingent on the total cost of ownership of a vehicle, which is an important component for the decision. And you see the representation of the optimal optimal fleet cost at time t equals 0 is dependent on the number of vehicles to be acquired and also the expectation of the minimum between both TCOs. This expression can be easily transferred into more analytic closed form, which we use to derive further results. And these further results entail important strategic implications for Laposte. On the left chart, you see the expected total cost of ownership per vehicle throughout time for both vehicle types. And where these functions cross is our expected break-even. Now you also see a small kink in the function of an expected total cost of ownership of an electric vehicle. And this is basically driven by the fact that the French government discontinues offering subsidy on the purchase of EVs at the end of 2013, which drives the price of an EV up. If we use this result, by using our analytic results, we can also derive the probability of the EV purchase throughout time. Now, for different policies, we can see this on the right chart. This probability function entails some interesting results for Laposte. For example, for the static policy, which is a dotted line, the probability of EV purchase jumps from 0 to 1 exactly at the time of the expected break-even. However, under the dynamic policy, which considers uncertainty in the model, the probability function is obviously smoother. We also notice that the subsidy for the purchase of EV has very little effect on the decision model. Now, for Laposte, the implication here would be, first of all, the expected time of the arrival of an EV, and also the time frame when the EV is to be introduced, in this case between 2014 and 2017. Now, if we put this together and derive the total costs and the total values for the 20 years of fleet operation, the expected total value of an electric vehicle for La Poste is a significant 87 or more than 87 million euros. So by using electric vehicles, La Poste would be able to save over 13% of costs. At the same time, we notice that the expected total value of the dynamic policy is fairly low, 1.26 million. Now, you might be asking yourself, why is the consideration of uncertainty has such a low impact on the bottom line? Let me show you the following graph, which represents the expected unit value of the dynamic policy. This is normalized for a single vehicle, and as you can see, the expected unit value of the dynamic policy has a significant impact only around the expected break-even between EV and ICV. If we superimpose that with the total number of EVs to be and ICVs to be acquired throughout my decision horizon, we arrive at this number 1.26 million. So actually, dynamic policy or consideration of uncertainty is only relevant close around the break-even, or the expected break-even. Further interesting result is that the expected value of perfect information, or basically knowing the future, is only 0.37 million euros, showing that the dynamic policy is very close to the lower bound. So we showed that the static policy provides a very good upper bound to our solution. Now the next question we ask ourselves, well, how does the static policy perform under model risk? Now let me give you the following example. Assume you studied, or we studied, certain technical reports in order to predict the development of the future battery price. And we come up with the following conclusion. A battery price process with a certain lambda and a certain expectation and confidence intervals. Now, assume that the actual battery price process follows a different lambda, lambda tilde, which we obviously don't know at time 2010. But we still have to make our decisions, and obviously these decisions will be based on our predicted lambda. As you can see, this entails significant risk to the decision maker. The fleet operator, La Poste, will be motivated by looking at this picture to follow the dynamic policy, because the dynamic policy allows us to reduce exposure to such risk by using recent uncertainty realizations. At the same time, the static policy provides an interesting trade-off. Due to this commitment at time 2010, the fleet operator would be able to achieve volume discounts and reduce administrative expenses, which aggregates to 10 million euros for La Poste. Now the question is, how do we quantify the effect of the model risk in terms of the different policies to be chosen? In order to do that, we use the notion of the expected downside risk and an underlying simulation approach, a Monte Carlo simulation approach with 10,000 trials, where we simulate the behavior of the model for different realizations of the battery price process under different policies. And we have some interesting results. On the left side, you see the expected value of an electric vehicle for La Poste for different policies. The one that I circled in green, which is the static policy with this fixed savings, provides a significant tolerance range for the realized battery price learning rate. As you can see, left and to the right side of my decision parameter, this range is quite significant. The same goes for the expected downside risk on the right side of the slide. So the interesting conclusion here is that the static policy, through the savings of 10 million euros, is very robust to such model risks. Now the next step was to translate this decision tool into software to support La Poste's fleet renewal decisions, which had nice interface and corresponding user documentation. But please allow me to let Alain discuss more about the implications for La Poste.
Thanks. So I am Alain Roset from La Poste. So during this modelization process, the steering committee of the mail division has to decide to invest in electricity vehicles. So a lot of exchange and a lot of discussion between the modelization team and the steering committee about the accuracy of the modelization and the results. So I take in charge this model and I implement some scenarios, because for my steering committee the central simulation is not enough. It's not enough because in 2005 we know that the mail will decline and we must test every investment to the decline of the mail. So I have to prove that in case of strong decline of the mail, the investment is always efficient and always good. So I take into the simulator and I try to implement some bank new scenarios. So first scenario, when your activity decrease, is perhaps to subcontract some part of your delivery network, rural part, because it's less efficient. So I test nothing about the break-even point, just 1 month, 2 months, 3 months of delay. So it's interesting. Second test, we decide to cancel 1 day of delivery. We operate today with a 6-day delivery per week. In some case, we can perhaps decide to deliver only 5 days. So a shift of 9 months, and we consider that it's not too dangerous to invest in a new technology with only 9 months of shift. Another question of the steering committee is, perhaps I have learned that IC motors can improve the efficiency of the internal combustion vehicle. So I test 30% of increase of the quality of the motor, the decrease of consumption of gasoline, with only 10% of increase in the price of the vehicles. And I observe a shift of 12 months, but only if the innovation occurs during the 2011-2013 year, because at the end of the focus, there is no impact, because clearly we are in electrical vehicles decision. But if innovation occurs in next year, but now we consider that it's not a risk, because we can observe that perhaps there is slight increase in consumption of vehicles, but as normal as usual, and not a break-even in the internal combustion vehicles technology. And the last point is a French point, because you know that in France we have a lot of tax on the gasoline, and we don't know, but perhaps government may decide that the tax on gasoline can be shifted to the electricity consumption for electrical vehicles. So I prove that it's a significant impact on the project, 2 years of shift in the break-even point, and we decide after these figures to have a lobbying group of electrical vehicles users to explain to the government that if the tax too much electrical vehicle during the 5-7 years of the beginning of the market, they will kill the market. And if you kill the market, you cannot achieve your goal to collect the taxes. So we prove that it's a very interesting simulation, that the evolution of the tax is more important than the technology in electricity vehicles field. To help the decision, we have built the modelization, and at the same moment we decide to bought 250 vehicles, prototype electric vehicles, to test in operation. So now we are 1 million of kilometers of test with electrical vehicles. I think that we have the most data accumulated about electrical vehicles in operation. And this test gives back precise parameters to put inside the model. And we study the reaction of the users of the vehicles. That means postmen and the first-line management. And it's very interesting. For postmen, it's very enthusiastic to drive electrical vehicles because there is no noise, a strong acceleration, there is no problems with ergonomics, and they are proud to be the first users of electrical vehicles in France and perhaps in Europe also. But for the first-line management, it's a little bit more difficult because they have to take in charge something new. It's a new economical model around the electrical vehicles. That means the cost of the ownership is very important because you have to buy the battery, very high cost of the battery at this moment, at the beginning, and your capital cost is very important, but your incremental cost, your marginal cost per kilometer is very low. It's just the reverse as the internal combustion vehicle now. Incremental costs are high and the ownership costs are very low. So just to explain to the first-line management was not perhaps make a lot of study of economical study, but I have to explain that you have to be sure that the internal combustion vehicles need to run less and less. You have to put in place electrical vehicles able to run up to 60, 80 kilometers per day, the maximum of the battery capacity. Because if you are above the battery capacity, your vehicle stops after the end of the day. So it's not interesting. So the next problem we are facing is our business model is basically based on mass market vehicles for the delivery. We are implementing mass market vehicles, that means lower price, and we are able to sell back after 6 years of use. So for electrical vehicles, we need to make sure that a mass market of electrical vehicles emerge in Europe or in France as soon as possible. So two solutions, two decisions. First is our CEO, Jean-Paul Bailly, has built a group of the larger users of fleet vehicles in France in order to write specification, common specification for small vans, for electrical vehicles, with this kind of specification as they have been written at the end of 2010. We have launched a tender, a common tender with all the users of electrical vehicles to choose more or less the same manufacturer. And at the end of October, of 3 weeks ago, we chose the winners of the tender, and we are now able to contract with Renault for 10,000 vehicles. So we are just at the end of the process, and we have signed the contract during the last week with Renault about 10,000 vehicles for the next 2-3 years. The first vehicle will be in operation at the end of this month. So first, try to have a mass market with a lot of different users sharing the same specification. And second one, we have launched a new subsidiary of La Poste with now 10 consultants, is a small subsidiary, to help the users to understand what is it electrical vehicles, what is the economical model behind these new vehicles, what is necessary to change when you implement electrical vehicles, all the change management for the users, and so on. And we help also the marketing division of the manufacturer, of car manufacturers, to understand how to sell electrical vehicles to new users. Two decisions to try to emphasize the volume of the market and try to reach a larger volume and lower cost for us. In conclusion, as André said, we can save 13% of operating cost for vehicles. Interesting. we can reduce carbon dioxide about 1/3, and we have enthusiastic postmen. They ask for new vehicles. They are asking for new electrical vehicles. So we can prove with this example that operational research is modelization, able to discuss with the steering committee and try make the bridge between the modelization team and the steering committee, try to explain what is a stochastic process, what is a stochastic price. Now I think we are at the beginning a new project, because we are trying to enlarge the market of La Poste in urban logistics. That means freight inside the urban area, to develop new market, new business, new revenues, instead of the declining mail. And now the technical team of La Poste are just in the cumbersome part of the project. That means they are trying to install plugs and wires in all the parking of La Poste and post office to refill the cars and electrical cars coming now. Thank you for your attention, and question if you want.